So, alright, just continuing from our inductive reactance, remember for purely resistive circuit, we know that resistance, so resistor. So, for inductor, we do not call it as resistance, but instead we call it as inductive reactance. Alright, so opposition to the flow of current, which result in continual interchange of energy between source and field of inductor. So basically it just wants to say that for resistance we usually dissipate energy in terms of heat and so on, but for inductor, right, they do not actually dissipate any electrical energy and so on. Alright, but of course we're assuming the internal resistance that's happening within the inductor itself. Alright, so that's part of the inductor bits that we will have to know about. What about the power? As you can see, like what we have mentioned just now, your I is the same, but your V is actually leading by 90 degree, right? Just as what we have seen in the phasor diagram just now. Alright, so this is just what's being shown for purely inductive load. Okay, energy stored in each quarter cycle is returned in the next quarter cycle. Alright, energy is stored on the positive side, and then after that it's released, stored and released. So if you actually count the average power, it would have to be 0. But this is for inductive circuit, something for us to just know about. Okay, and for you to get the power, alright, as we know that power is actually your V and I, right? But in this case, since it is inductive circuit, alright, so we have, for purely resistive circuit, then we have the power, right? For resistive circuit, the power is also what we know as real power or true power. So please remember that, yeah? If it's inductive circuit, we actually call it as reactive power, alright? And it's actually, for resistive circuit just now that we looked at is actually denoted by capital P, right? Capital P equals to VI. But in this case, it's also still VI, but the representation is called differently now. For inductor, right, anything to do with inductor, we call it reactive power. And reactive power here is denoted by QL, alright? And if you notice, like earlier we see that P is equals to VI equals to I square R equals to V square over R. That's for resistive circuit. But if we're talking about inductive circuit, everything stays the same, but remember, we do not call it resistance, we call it reactance, denoted by XL. Alright, and just remember that for my reactive power for inductive circuit, this is the unit for it, reactive volt ampere, or what we call as VARS. Okay, so that's something for us to know. Whereas for power just now, for resistor, remember, we call it real power, true power. It's actually in watt. Okay, but for inductor we call it as VAR, VAR. Yeah, now we move on to capacitor. Alright, so capacitor, in a way, it's kind of related a little bit to your inductor, alright, but over here it's actually for capacitor, right, it's actually able to store electrical energy charge. Alright, and sometimes you want to use it for blocking some DC signal. Alright, you want to allow some signal to pass, some signal not to pass, and so on. Power factor correction, this is actually kind of interesting. Alright, we will look at the efficiency of electricity and things like that, and later on we will see what can be done to do some power factor correction to make it more efficient. And in this case, to make it more efficient, we actually use the usage of capacitor. But this is for another topic, I think, for the next topic that we're going to look at later on. Alright, so this is some other application that we have for capacitor. Okay, so if you look at it, just the same thing. Alright, in this case, how it is being related is that your I across capacitor is also known as C dV dt. Alright, with all the derivation that goes on and all that, you know that C, capacitor, is in farad value. Alright, this is actually a capital F, so it's a typo, yeah. Alright, So we also know this as, remember, unlike resistance being known as R, reactance for inductor XL, for capacitor it's also called reactance, but we know it as XC. Okay, so 1 over omega C. Omega is actually 2 pi F, just like what we have mentioned just now. Yeah, so this is the important thing that you will need to remember for your capacitor. Alright, the unit itself and then how you get the reactance. Okay, so this is what we have looked at. I think, have we? Okay, we've talked about this and then we talk about this. Alright, also the same, the behavior is the same as inductor. It does not dissipate energy in any form, unlike reactance, unlike resistance. Alright, so there's a difference here with inductor though. You see here, over here, current always leads voltage by 90 degree. For inductive circuits, it's actually the other way around. It actually lags by 90 degree. So if you look at it over here, just like I mentioned earlier, if I actually just draw it out over here, alright, so this is where it starts, this is where it starts. My current actually starts earlier than my voltage, therefore my current actually leads my voltage. And by how much? If it's a purely capacitance, alright, it always goes by 90 degree. That's just how the behavior goes. Yeah, so this is how some differences of capacitor and inductor. Alright, so by now you actually learned some terminology on capacitance, inductor, the behavior, and then remember, because your current actually leads your voltage, right? So it actually is the mirror image as compared to your inductive circuit just now. So it doesn't have to be necessarily every time like a straight perpendicular line here where it lies on your x-axis and y-axis. It can be of certain shape like this as well, alright, where this indicates that your VC is of a polar form of negative 30 degree, and if it's a purely capacitance circuit, definitely your I is going to be of 60 degree over here. How do I know it's 60? Because I always know that for purely capacitance circuit, my I will lead my V by 90 degree. Alright, so it can be of this shape, it can be of the other shape. Let's say if my V is 20 degree for example, then my I will eventually be 70 degree difference. Alright, you just know that for all that these two being summed up together, it will lead to 90 degree in total. So that's what's important here. Alright, so this is just sort of like a notation for us to remember. Alright, for capacitor circuit, if you can remember ICE, alright, for capacitor, the current will always lead the voltage. Voltage being denoted as E here. Alright, LE, this for inductor. Inductor voltage leads the current. So if you can remember one, you can remember the other one, because the other one is just the opposite of it. Alright, so now we go to impedance concept. Impedance concept is when you have a combination, alright, of your resistance, can be capacitance, can be inductance and all that. Alright, impedance is still being measured in ohms. Alright, so V equals to IR, remember, so instead of R we use it as Z. Okay, so impedance can be of, just like I mentioned just now, resistance, capacitance and inductance. Alright, so for purely resistance and all that, your impedance will basically just be R, nothing changed over here. Okay, if it's inductance and all that, you see how it is being calculated. Your ZL will basically be your J omega L. J omega L basically your XL here. Yeah, XL is omega L, which is also 2 pi FL. That's how you get your inductance for your the reactance for your inductance or your XL. Alright, do remember that.